Welcome to AMS Weatherband's latest webinar. This is Winter Lake Effect Systems, Scientific and Educational Adventures to Further Our Knowledge and Prediction of Lake Effect Storms. Now, I would like to introduce today's moderator. So thank you, Dr. Bhimmareddy, for joining us and for moderating the webinar today. Dr. Sudhir Bhimmareddy is a research scientist with the CERES, is it CERES? Am I saying
CERES, yeah.
CERES. At CU Boulder and Global Systems Laboratory of NOAA since November 2023, specializing in lake effect storms and cloud microphysics with a PhD in mechanical engineering from the University of Texas at San Antonio. And so, yes, Dr. Bhimmareddy, I give you the floor. Thank you very much.
Thank you for the introduction, Gideon. Good evening, everyone. I know it's late at some parts of the world, so we'll try to keep this short and quick. So today's session, we'll be discussing one of the most fascinating weather phenomena that I like personally because I like snow, is the winter lake effect storm systems. And I'm from India. We don't have many of these lake effect storm systems. So when I came over to Illinois, I was fascinated by the project, which is OWLS and Lake Highs, that some of the panelists will be discussing today. The data, the extensive observations that were collected during these campaigns. So the main topic of today's session is to discuss some of the scientific adventures and also to further our understanding about the lake effect storms itself. So with that, I would like to introduce our panelists, starting with Bob Gates. Dr. Gates is from Department of Atmospheric Sciences from University of Wyoming, and David Kristovic, who is my postdoc supervisor. He is from Illinois State Water Survey from Prairie Research Institute located at UIUC in Champaign, and Justin Minder from Department of Atmospheric and Environmental Sciences from University of Albany, Vanna Muleski from NOAA National Severe Storms Laboratory, who is working as a research physical scientist. Finally, Jeff Frame from UIUC as well, Department of Atmospheric Sciences. With that, I would like to introduce welcoming remarks from Richard Clark from Millersville University, and who is also AMS immediate past president. Over to you, Rich Clark. Rich, you're muted.
Thank you, Sudhir, and welcome everyone. And I understand that we have a really large audience with us today, so I'm going to get right into it. Each of the panelists will have about 6 minutes to present some stuff, and then we're going to open it up to Q&A. And you know, I'm just going to start by saying this: that of the 35 years that I've been sort of in this business, there has nothing been more exciting for me than in 2013 and 2014 to take 26 students up to the Great Lakes area, Ontario Lake area, and participate in Ontario Winter Lake Effect Systems study, and just be pounced by the winter storm events. We had, I think, 23 or 24 intensive operation periods, and we were supporting two different locations, one near Geneva, New York, and the other in Sandy Creek up near Tug Hill. And so we're going to be talking about those kinds of things and others today. I'm going to get started by putting up a slide that shows today. This is January 17th, a satellite view from this morning. We had west-southwesterly winds, so we had strong winds up to 34 knots. Here they are in this area. You can see the winds right here in the wind direction. So we had strong winds along the long fetch dimension of both lakes. And so, Buffalo and again, Tug Hill are affected by that. And I put this slide up to include all of the Great Lakes because the weather that actually affected these two areas, the Lake Erie and Lake Ontario, was actually modified by air that had come down across various other Great Lakes, and it modifies the entire boundary layer. And that was something that was really of interest to us. Here's a snow amount ending for 7 p.m. tonight, as of right now. And so again, Buffalo and Tug Hill area are sort of getting pounded upon. But not all of the lake effect snows are this long fetch type. Sometimes when the winds are out of the north, they do the short fetch crossing of the lakes. And if it comes down across Lake Ontario, you'll get heavy snows in Rochester, Oswego, places along this lower shore into the Finger Lakes region. And what's most interesting, and there's been some of the studies on this, is the propagation of lake effect storms way down into even southern Pennsylvania. Now, I had to add a couple more pictures, one from January 14th, which is the Highmark Stadium. And maybe the Steelers should have played that night and they would have won. The major Steelers fan, and I was really saddened to see what happened to them. And then this is just downtown Buffalo, this other photo. So that's real-time conditions. By the way, wave heights were up around 14 feet as a consequence of the wind speeds across the long fetch dimension. So this, I put up a logo for owls. That's what it looks like. And the QR code there, if you're interested, if you want to grab some of the references in the special edition on the Ontario Winter Lake Effect Systems article, peer-reviewed articles, you can get that there. So what I'd like to do is just go talk a little bit about some scientific questions. I'm going to go through these rather quickly because the other panelists will talk about this. Now, what makes the lake effect systems PBLs different, planetary boundary layers different than other PBLs? And it's such a rich interplay between the thermodynamics and the dynamics and the microphysics and the electrification processes as they develop over the lakes. And it's just such an interesting study of these multiple dimensional amalgam of atmospheric processes. So, and also, how do they differ? We have the conditions where there's the short fetch where it comes across the lakes and puts snowfall down into the Finger Lakes area and further propagation. And how does that differ from the snow that, the air that follows the long axis of the lake and dumps its snow in Buffalo if it's coming across Lake Erie, or Tug Hill, New York if it's coming across Ontario? How do these convective structures persist far downstream? I mean, they leave the buoyancy source. So what maintains them? And we've done some studies on this. And we have these elevated mixed layers and differential advection with cold air advection aloft, and that helps to sustain all of that. And we'll be talking about that today. Of course, there's interactions between the lake effect systems and the downwind shore topography. And of course, Tug Hill's a little higher than other regions around Ontario, which is why they get significant, these extreme snowfall intensities and snow accumulations. We had a large crew. And so we were studying everything from surface fluxes to convection, advection, the horizontal rolls, all of the things that are listed right there. And each of the panelists will delve into those things in various degrees of detail. I want to finish with a couple slides here because you couldn't do a project like this without the help of students. And one of the most wonderful things, wonderful experiences I've had in my life is working with dedicated students. Here's my favorite picture of all time. 3 students, 3 o'clock in the morning. Wind speed was -55. The wind chill was -30. Heavy snow, and they're launching balloons. We had to put hot hands around our signal processing unit in order to keep it warm enough so that it wouldn't die. And then off to the left, you see a couple students there who have just been shoveling out our trailer that was up at Sandy Creek. And it's just wonderful working with students who are just passionate. No matter what happened, there was still a smile on their face. And I'm going to end with this slide here. Not only were our students involved in doing radiosonde launches and tethered balloon launches and running an acoustic SODAR and all of that, but they also, along with the help of the University of Wyoming, took 11, I think this number is right, I haven't verified it, but I think we took 1,100 ice crystal photographs. These were taken mainly by Mike Charnock, who's now the Sioux out in Cheyenne, Wyoming. And you'll see a beautiful array of just some of the things, the more subtle things of lake effect snow. So that's all. I'm going to stop my screen here. Bart Geertz from the University of Wyoming is going to pick it up. And thanks for listening.
Thank you, Rich. So yeah, I'd like to step back and think about how do these lake effect snowstorms develop. And really, in general, it's an air mass transformation process where air from land, or in this case, from the Arctic ice edge,
You're not sharing the slides, Dr. Gates.
I'm not sharing.
Yeah, we are seeing the other screen.
I think you're sharing, but not
The wrong- yeah.
not the
Presentation,
Google
it's not.
Slides.
Let's see how this goes.
There you
There you
go.
go. There you go.
Perfect.
All right. Yeah, sorry about that. So, but cold air moves from the Arctic ice edge in this case, or from the continent in the case of lake effect snow, over open water. And then you can see these tremendous surface heat fluxes. Basically, sensible heat flux is about as large as you can find it anywhere on Earth. Tremendous temperature contrast, maybe 20, 30 Fahrenheit between the sea surface or the lake surface and the air above. And that triggers convective motions. At first, very shallow, but intense, vigorous convection, lots of turbulence. They then organize in the form of helical roll circulations. And with the addition of moisture from the open water surface, there's a large latent heat flux component as well. That moisture will then condense, produce cloud cells, essentially convective cells that line up, that tend to basically be amassed to converge towards a convergence point, driven really by these roll circulations. So you get cloud streets. And then, as the satellite image shows, these cloud streets eventually transition towards open cellular structures. This is a very characteristic and, in my mind, a very beautiful depiction of these I guess, marine cold air outbreaks, which is essentially what lake effect snow is. Sometimes you get open cells, sometimes you get closed cells. And one of the questions in the Q&A is about, what outstanding questions still exist. Certainly when it comes to the marine cold air outbreaks, the cellular structure, open versus closed cells, is one aspect of uncertainty, the organization of the clouds. There's a vertical transect shown below from spaceborne LiDAR and radar below that, just to show how the boundary layer deepens as a result of these surface heat fluxes, and the clouds develop, producing that backscatter. And then reflectivity increases, indicating that snow is produced, and some of that snow, of course, falls over open water. But then when there's downstream topography, as is the case here with Norway, there's enhanced snowfall, orographic effect that I believe Justin will talk more about. So this cloud regime is actually fairly common, and occasionally you can see some spin up, some convergence line may produce some vorticity, and you may get a polar low that sometimes has an eye-like core, almost a hurricane-like structure, but usually is fairly baroclinic. These are small mesoscale cyclones with limited depth because the tropopause is so low in that very cold air mass. Sometimes multiple polar lows will spin up. They have a lifespan typically less than a day, 24 hours. And they can be quite intense and produce a hazard for maritime operations and along the coast with strong winds, gale force winds, and also heavy precipitation. Now, these cloud structures are rather ubiquitous. You've seen these cloud structures off the east coast of the US after the passage of a cold front in the cold season. Characteristic cloud pattern, cloud streets involving interstellar structure. There's an example on the right from the area of the Black Sea into the Mediterranean. Another example from Japan in the lower left. And then the Great Lakes of North America produce the same type of cloud patterns. So lake effect snow really fits into this same category. I want to spend just one slide looking at lake effect snow in Japan. You can call it sea effect snow. The Sea of Japan is relatively warm. It's actually warmer than the Great Lakes typically are towards Japan. Temperatures as high as 14, 15 Celsius in December. And at the same time, Siberia is one of the coldest places on Earth in the winter. So you get tremendous temperature contrasts, strong heat fluxes produce the same characteristic cloud pattern. And then Japan also has terrain over its main island and towards Sapporo in the northern island. And that produces much of the snowfall that Japan gets. Its typical frontal system produces relatively little snow. Most of the snow comes from this post-frontal lake or sea effect snow, and there's a specific area they refer to as Kosetsu Chitai, the heavy snow region, really can get massive amounts of snow, as documented by Jim Steenberg in a number of papers, including an overview paper in the bulletin. Going towards the smaller scales, Lake Ontario, the OWLS campaign that Rich talked about, the short fetch or cross lake snowbands, they have essentially the same structure, cloud streets. The distance is not quite enough to produce open cellular clouds. But essentially, it's a rapid air mass modification process whereby the boundary layer becomes well mixed in the lowest kilometer or so. Strong heating at the surface is evident. And that produces these clouds, some of which produce relatively high reflectivity, as seen with our cloud radar aboard our University of Wyoming King Air that you see in the lower left. We flew across these bands in OWLS, and you can see some interesting convective cells. So these cloud streets are essentially a series of convective cells that have been aggregated, I guess, along these convergence lines. And then when the wind is not from the north, but rather from the west-southwest along the lake, then you get some interesting shoreline effects. A land breeze front may form, or maybe multiple land breeze fronts. And
sorry. Yeah, time's up.
Okay. And that leads to some convergence lines that Justin will talk more about. And on the very small scale, you can see some lake effect snow even over the New York Finger Lakes. I'll leave it with that. Thanks.
Thank you. Right. Next is Dr. Kristovic.
Okay. Okay, can you see my screen? Okay.
Yes.
Great.
You can see the presentation.
Let me get down to get past Bart's great presentation here. Okay, great. Well, I'm going to talk about a couple of field projects, but there's been a long history of research on lake effect storms going back to the 80s and certainly well before that. There are records in the 1800s of people discussing lake influences in the Great Lake, in Chicago area, for example. I'm going to talk about observations from the OWLS project and the lake-induced convection experiment, or lake ice. First thing to point out, Rich mentioned already, lake effect fundamentally is a boundary layer process. And this is just a cross-section of isotopes where the air is flowing from Wisconsin, cold air is blowing over Lake Michigan and coming onshore in the Michigan side. And as the air moves from left to right across here, you can see the isotopes are becoming more and more vertical over a deeper layer. That's just reflecting the growth of the boundary layer as it moves across the lake. Now, the shaded area is, on this particular day, the clouds that we observed over the lakes. It's amount of area covered by with snow observations, and see some interesting things. First of all, the clouds more or less filled the boundary layer out up near the up western shore of Lake Michigan, and the clouds become more narrow as you move across the lake. This is something we've seen multiple times, and it's a little surprising since the air is over its moisture source, which is the surface. And one of the reasons for the clouds becoming thinner is that some of the moisture from the clouds is going into the development of snow, which is in the lower panel. And as the snow becomes more and more, fills the boundary layer more and more, and it gets mixed throughout the boundary layer with all these circulations, it tends to eat away at the clouds. But that's not really enough to account for why the clouds decrease so much, and we'll get to that in a little bit. Now, we've done a number of studies trying to understand lake effect snow. This is the same kind of pattern where we have the left panel, the left side of the panel is Michigan. I'm sorry, is Wisconsin. Cold air is blowing from left to right and reaching the downwind shore on the right-hand side. This is from a study a few years ago by a student who found some interesting things. One is that the number of snowflakes out there tended to decrease after you got about midway across the lake. And that's when the snow particle growth changed from mainly deposition to aggregation of snow particles into clumps that we call snowflakes. Important evaporation below the cloud deck. And if there were no entrainment of dry air from above the boundary layer, it's hard to explain any evaporation occurring below the cloud base. So entrainment is a big player in the growth of the boundary layer, as well as things like evaporation. Now, if you look at this more quantitatively, we're asked the question all the time. You have all this vapor being tossed up in the air from the lake surface, evaporation into the air. How much of that is being dumped back down into the lake? And there aren't many studies of this, but this is one that we conducted where we found that in these cases, about half of the amount of vapor going up into the air is being dumped back into the lake. So lake effect is a drying process. It's actually not a moistening process from the standpoint of the lake itself. The lake effect tends to reduce lake levels. That's surprising at first, but that's something that we see over and over again. So how can we make our snow heavier? And one way is to have upwind lakes. On the left, we have a lake effect storm reaching Lake Erie, blowing across over Lake Ontario. And you see some very interesting things. The clouds develop closer to the shore within the Lake Erie plume as compared to on either side of the lake effect plume. And if you look on the right panel, this is radar and LIDAR observations, you see that there's a dramatic change as you go from the Lake Ontario only lake effect to the Lake Erie plume, where there's very, very heavy snow. And the cloud patterns, the clouds themselves change, as you can see from this LIDAR image on the bottom there.
1 minute left, Dr. Christoph.
Okay. Another way is to have elevated mixed layers. Earlier studies recently have found that the upwind lakes can give these. We also have observed elevated mixed layers that are associated with cyclones moving over the Great Lakes. And this can greatly increase the amount of snow that you get near the out over the lake in areas where they're going on. Another way is related to pushing this lake effect air up over mountains. And that's going to be our next speaker.
Thank you very much.
All right, can you see my slides and hear me okay?
Yes.
Okay, thanks. So I'm going to speak to you briefly about two topics. The first is, how do coastlines and topography affect lake effect storms? So we've got a little schematic of lake effect cloud developing over warm water. And then I'm interested in talking about what happens when it reaches the coastline, interacts with the coastline, that water to land transition, but also maybe interacts with topography, mountains or hills on the other side. So this happens a lot downwind of Lake Ontario, a region we focused on during the OWLS campaign, where the Tug Hill Plateau sits. And if you look at these red dots, which show locations of co-op weather stations, this is showing the average snowfall at these locations. You see these stations up on Tug Hill receive almost twice the snowfall of the surrounding stations, suggesting that maybe the lifting of these clouds over this terrain barrier really strongly enhances the snowfall. And we might ask, why is that? What processes are going on in these clouds to give us so much more snowfall over Tug Hill. And here's some schematics of some of the things that could be going on. Maybe the clouds are getting deeper with stronger vertical motions to give them more snowfall. Maybe they're getting more tightly packed together. Maybe there's less subcloud sublimation going on, and so on. There's a number of possibilities that we wanted to explore during OWLs. And one of the ways we did that was by putting these vertically profiling radars, MRRs, they look like the one in the photo here, at several locations going from the coast up onto Tug Hill. And I'll show you data from these two starred locations here. The top panel is showing you data from that coastal location, whereas the bottom one is from the one up on Tug Hill. And this is a time versus height graph of radar reflectivity. So time goes from left to right and height goes up and down. And the shading is showing you the radar reflectivity. So redder colors, think more snow and bigger snow particles. So we can see at the coast, you see those redder colors indicative of maybe heavier snowfall rates and also taller clouds. Yet as we move inland, the tops of those echoes get shallower, and it seems like the precipitation is getting less intense, but it's also more continuous. So one thing we learned here is that it's not an invigoration, a strengthening or a deepening of these clouds that causes the enhancement of snowfall over Tug Hill. It's more some combination of these other mechanisms, and so we investigated that in this cited study here. Another thing we looked at, or that was looked at in the project, was the role of coastline boundaries and how they influence the lake effect snow pattern. This is work led by the University of Utah, Leah Campbell and Jim Steenberg. And they did a lot of trajectory analyses, they did WRF simulations, they did observational work, and they really found that these frontal boundaries that occur where air that passed over the lake and got warmed meets air that didn't pass over the lake and stayed colder. These are really important in organizing the snow bands and enhancing regions of snowfall. And this region of Tug Hill just happens to be where some of these boundaries, these frontal features come together and would enhance snowfall, likely even if there was no terrain barrier there. And they actually showed that using numerical experiments where they removed the Tug Hill. So that's another interesting result that came out of the project. The other thing I'd like to briefly talk to you about is what processes go into predicting lake effect snow. And we predict it often using high resolution numerical weather prediction models, but there's some processes in those models that are particularly uncertain, such as the turbulent air motions that transfer heat and moisture from the water to the atmosphere, and the turbulent motions that further transport those quantities up through the boundary layer, and also the small scale processes whereby snowflakes grow and fall out of the atmosphere. And so these are some things I've been looking at in my group as well, trying to understand how uncertainties in those processes affect uncertainties in our forecasts. And these are 4 different numerical simulations of a lake effect snowstorm over that Tug Hill region. And the only thing that's different between them is using a different so-called parameterization to represent the turbulent fluxes off of the lake and into the boundary layer. And you see that depending on which of these parameterizations you use, you get really big differences in the amount of snowfall over the region, shown by those different color shading. And we found in comparing these, the reason for these big differences is these different schemes yield very different fluxes of heat and moisture off of the lake. And that's what's shown in this color shading here. This MYNN scheme fluxes much less heat from the lake to the atmosphere than this QNSE scheme. And as a result, the lake effect convection is weaker and dumps less snow over the downwind terrain. We actually found that this MYNN scheme seemed to perform more realistically when compared to observations relative to this kind of hotter QNSE scheme. And the last thing I'll mention is we also looked at some of these uncertainties related to the microphysical processes that go on in the clouds. Here's a simulation of the same lake effect snowstorm over Tug Hill region. This is work led by former grad student Massi Bartolini. And what he did was he redid those simulations, but perturbed assumptions related to the snow crystals, basically changing from faster falling snow, more representative like needle-like crystals, to slower falling snow, more representative things like dendrites. And when you do that, the color shading here is showing you the difference from what you get in that control simulation. And when you have crystals that fall faster, this blue shading is showing they dump out closer to the coast and give you heavier snowfall rates on the Tug Hill and near the coast. Whereas if you have the slower falling dendrites, they stay in the air much longer and they decrease snowfall in that region and increase snowfall downwind over the Adirondack Mountains. So this is another important uncertainty to consider in our numerical models when we're trying to represent these storms. Okay, I'll stop there and pass it off.
Thank you very much. Next is Dr. Milowski.
Yeah, can you see the presentation? Hear me okay?
Yes.
Okay, wonderful. Hi there. Yeah, so I'm going to talk a little bit more about looking at things downstream of Lake Ontario and look at the Lake Effect Electrification Project, which happened over last winter season. So we're actually looking now instead at how these events actually produce lightning. I specialize in lightning observations and research, so a little bit different than just the snowfall itself. For anyone who's unfamiliar with electrification in clouds in general, we know we need a few ingredients. We need some sort of snow and ice crystal, a heavier ice particle like graupel or hail, and it's really efficient if we also have some super cold liquid water droplets around that can help make that electrification process a lot faster. The different particle interactions interact, separate charge, they move differently in the cloud, and eventually we get these charge imbalances that produce lightning. We have a lot of questions about electrification in general in any sort of thunderstorm, but in lake effect snow, there's really a lot of unknowns. We don't really know what sort of particles get what charge and where they end up, what layers and how they arrange, what are the minimum conditions that we need in order to get that lightning flash to even start. Really just lots of questions there, which are some of the things that we're trying to answer with the LEAD project. We've already talked about the Tug Hill Plateau. Thanks to everyone before me. So we already know there's a lot of snowfall that happens there. One of the other interesting things that happens though is there's also a lot of lightning that happens on the Tug Hill. And one of the factors over there is there's a lot of wind farms that have gone in. And a lot of winter lightning, regardless of whether it's like snow or something else, tends to be triggered by something on the ground. So the question is are the wind turbines triggering lightning that wouldn't happen otherwise? Are they just ending up there because they're at higher elevation anyway? So these are the sorts of things that we're trying to study. So to do that, we took a lot more observations. We had a lot more students out in the field with us shoveling snow and doing a lot of other observations. So the first things first is our lightning observations. We set up what is known as a lightning mapping array, which is an array of radio sensors that we can use to actually map out the path that lightning takes within a cloud in 3 dimensions. And there's a couple examples of what those stations look like. And we set them up all around the Tug Hill. So we had good resolution of any lightning that happens on the Tug Hill. And those were operated continuously throughout the season. So any lightning, regardless of whether or not someone was there, we captured. We had one of the Dow radars up there. And then we were also launching a lot of balloons. So we had environmental radiosondes launched in Oswego just to get an idea of what the background environment was. An electric field meter that we were launching into the snow bands themselves. So we knew what the electric fields in the snow bands that may or may not produce lightning look like, because we don't know what they look like. And also some particle imagers so that we had a better idea of what particles are involved in the production of those electric fields there. We had a lot of vehicles that were out there doing our ballooning observations and a lot of students. So we also had good observations of the snowfall at the ground wherever we were. So we saw some very large graupel, finger for scale, very scientific, and a lot of different sorts of snow patterns on the ground. So observations of all of those and what produces lightning. So a few fun examples. So last season, November, there was a really good lake effect snow band case over there. We had a really warm lake. The land surface was just above freezing where we were, which was just downstream of the lake. Our snow growth zone, only a couple kilometers up, and our entire cloud was within the mixed phase region. So we might have all of those different cloud particles interacting with each other, electrifying. Shown here on the right, all of these lines are the electric fields that we measured with some of those giant balloons. Where there's red, that's where we saw positive charge. Where there's blue, that's where there was negative charge. So we had positive charge at the surface. How deep that was really varied depending on what part of the snow band we were in at the time. Above that, there's negative charge, and then above that at the top of the snow band, we saw positive again. In the lightning world, this is what's known as a normal tripole charge structure, which we were not expecting to see. This is what you see in tropical convection in Florida at a very different altitude. But that's what we were also observing in the lake effect snow bands too. This case itself was producing about a flash an hour on the Tug Hill, so a little bit farther inland than the sounding here. So very interesting case. And here's an example of sort of what that lightning mapping array data that we collected look like. So here's a radar cross-section just from the 88D. All these little black points are points that the lightning was emitting that were observed by the lightning mapping array. So you can think of them like little sections of the lightning channel that we're capturing by the radio waves. So together they all map out the path the lightning takes.
1 minute left.
Our pink line is our balloon that went up there. We have our reference temperature levels, and our lightning flash started over here on top of the Tug Hill on the north side. Not that there's any real labels here. And with the way it was propagating, we know it was a negative charge, so that agrees with our electric field soundings. And then it actually propagated upstream towards the lake, which is pretty cool. Saw some upward flash development, and then it went above cloud and eventually back down into the cloud itself. If you've ever looked up at a supercell anvil and seen what's known as spider lightning, where you see lightning underneath the cloud, we're seeing the exact opposite thing on the snowband, where our lightning was actually traveling above cloud and then back in. And we saw this actually quite a few times throughout the project, which was really pretty cool. For another perspective, here's an example from the Dow. I will quickly wrap up. I will go ahead and skip that, but you can see it hugging the cloud. And in general, if you want to have some exciting weather, maybe never plan a field project. This is the driest winter on record in Oswego, so kind of failed on that. But we still ended up with 11 observation periods, 3 of which produced lightning. And a good third of them were definitely triggered by those turbines or other towers, and lots and lots of ongoing work on that. And I will hand it back off.
Thank you very much. Next is Dr. Frame.
All right, let's get started here. Okay, so I'm going to provide a bit more of an overview of the OWLS project, what it was like, and then talk about some of the vortices that we see in these lake effect snow bands. We really had an embarrassment of riches during OWLS, planning for 14 IOPs, having 23. A big reason for that was successive shots of cold air from Canada down across the Great Lakes. These are just the temperature anomalies for December and January of that year in degrees Celsius, so roughly double that to get degrees Fahrenheit. A couple big events, December 10th and 11th here. Some areas of Tug Hill getting up to 4 feet of snow. I don't know what you do with all that. And then, not to be overdone, but January 5th through 8th, again, some areas here, 4 to 5 feet of snow off Lake Ontario. This, of course, was the massive cold air event in early January 2014, if you remember it. But one thing about that was the one that unfortunately popularized the term polar vortex. We don't want to say that. What do you do with that much snow? This is one of our students, now Dr. Amanda Chasteen out at NCAR, standing almost waist deep in all of this. Of course, driving conditions, driving across these bands and mobile mesonettes and instrumented vehicles, sometimes very, very bad. And you say, what was it like? Well, it was a lot of cold wind, snow, and dark. And we would have daily, almost daily meetings where we would examine the forecast, make our own forecast in collaboration with folks from the Weather Service in Buffalo. Here we have a large, diverse group of students working on different things. I see at least 3 or 4 people there with PhDs now. And we'd plan out where all of these assets would go. We had 3 mobile Doppler radars, numerous snow observation teams, mobile radiosonde launches, and all kinds of things. And of course, our goal was also to construct dual Doppler analyses of this. And given all the tree cover and hills in upstate New York, really the only place we could do that was along the lakeshore. Here's a picture of one of the Doppler on wheels in action. Not snowing there, but snow off in the background. Not shown here, though, is sometimes we'd have to shovel out the deployment sites. When you have 2 or 3 feet of snow, right, they just kind of plow it up there, and this is our famous road end sign there on the eastern end of Lake Ontario. But the Dow data really afforded unprecedented spatial and temporal resolution. Here on the left is just Weather Service NWS 80 or WSR 88D data. Pretty coarse here, scanned maybe every 5 or 10 minutes. Whereas with the Dow here on the right, much finer in spatial resolution. Also temporally, where we would get a volume scan about every 2 or 3 minutes. We also had portable weather stations, sometimes known as tornado pods. We would pre-deploy these and drop them off so they could collect in situ surface observations. University of Alabama in Huntsville brought their MIPS, a mobile integrated profiling system here, and this is some of the data they collected from the ground within a band that's timed there on the horizontal axis. We also had a University of Wyoming King Air, thank you, Dr. Gertz, and these often flew in lawnmower-like patterns across the band. And in these data, again, we saw all kinds of things. Reflectivity here is on top, radial velocity is on the bottom, and down there below 1 kilometer in the radial velocity field, we have a lot of just boundary layer convection and turbulence showing up. And then up at the top, generating cells, and then deep convection over there, 2325, 2326 over on the left-hand side of that. This is just a view from the aircraft. But what does a lake effect storm look like when you look into it? Kind of looks like a thunderstorm. And then do a vertical scan through that. Well, I'll be darned. That's an anvil. So yeah, these things are convective, and then just instead of the top being the tropopause, the top is just the capping inversion atop the cold air mass, which, well, sometimes it is the tropopause if it's right. And kind of continuing on that same theme, here's a picture from Dr. Scott Steiger at SUNY Oswego looking out over Lake Ontario and just looking there, that rain-free base, it kind of reminds me of something. I spend a lot of time also on the Great Plains observing things as part of a field course. This, just random day, May 31st, 2013 near El Reno. I'm sure nothing happened. But you notice the similarity there kind of between, almost supercells and some of these lake effect structures. And indeed, looking at our dual Doppler data, solid contours on this are vertical vorticity, and the shading is stretching term. And if you look closely, you see a horizontal wind shift there along that band, with stronger winds to the south because of low pressure in the center of the band, weaker winds to the north. That yield a sheet of cyclonic vorticity, and then that would break down due to horizontal shearing instability. The criteria were met along that wind shift, break down into discrete vortices that would then strengthen via stretching. This is a zoomed in view of this now. Zonal wind on this is shaded, but again, that wind shift very clear there in the middle of the band. This courtesy of my former MS student, now Dr. Jake Mulholland at the University of North Dakota. And I know some of you were wondering, and the answer is, am I going to show a picture of a tornado? The answer is yes. This is a picture of a waterspout over one of the Finger Lakes during Owls in Ithaca, New York. Now, how many of these vortices actually yield waterspouts out over the lake? That number really unknown, and I'm not sure how you would answer that, since during peak lake effect season, November, December, and January, it's dark about 2/3 of the time. And of course, you can't see through snow very well either. But I know there was one other instance up near Erie, Pennsylvania, where some storm chasers did visually document a waterspout up there over Lake Erie in that case. And that's all I got.
Thank you very much, Dr. Phil. That's a wonderful session. And we have some Q&A typed in by the audience. Does anyone want to answer them? Shall I read them out loud? Oh, you are answering them, okay. So Alan Hall asks, does the relative lowering of the clouds to the Tug Hill region drive more lightning strikes to Tug Hill? Looks like a interesting.
Yeah, I can go ahead and address that.
Sure, yeah.
So that's actually one of the things that one of our students is really doing a lot of research on right now, is looking at which ones were producing lightning and which ones weren't. And there does seem to be a big pattern as to where you start losing the depth of your snow bands. And if it was over an area like the Tug Hill, where there are a lot of the wind turbines, communication towers, and everything else, if you started losing that depth, there is where we started seeing more lightning flashes. Still more investigation going on that, but there does seem to be a pattern there.
Thank you. Does that answer your question, Alan Hall? Can I just close that? Okay. And then Calvin Maid asks, what is the correlation between the upper and lower level winds over open water for enhancing lake effect snow? Wow, that's a deep question there. And does wind shear in the upper levels, such as 500 millibar and up, for example, play a crucial role in the capping the intensity of the snow bands, or perhaps creating more consistent widespread snowfall on the land? That's my last year's work, actually, right there.
Well, go ahead and answer it then.
No, I don't want to run into any controversies. Go ahead, Dave.
I mean, I can make an initial stab at that, but there are others here that can go into it further. Certainly, this is an understudied issue. Certainly, the density of snow, the liquid to snow ratio, the snow particle density, as well as other things. It's really is an understudied avenue, and I really do think we need a lot more in situ as well as remote sensing snow particle and cloud liquid water measurements within the storms. One thing about the shattering or the breaking of snow crystals, I know that can happen at the surface, especially with strong winds. Also, collisions between snow particles and liquid water particles can cause shattering of snow particles. And so there's quite a lot of work on that, but not necessarily in lake effect.
And also going more in the shear in the organization is that if you have a lot of directional change in the wind with height, and the wind is changing direction, that tends not to be as favorable for lake effect snow. Also, if the wind shear is too weak, the winds are too weak, the bands just will form over the lake and stay there. They won't move over onto land. Kind of another factor we saw kind of related to the larger scale environment is that the same areas where you see synoptic scale ascent, like, for example, downwind of shortwave troughs in areas of differential cyclonic vorticity advection, that large scale ascent in the mid-atmosphere actually helps deepen the boundary layer and leads to a localized enhancement of the snow in regimes of synoptic scale ascent. Now, the synoptic scale ascent, of course, not directly responsible for the lake effect snow. It's completely convective. But that background ascent, just like in severe weather environments, can certainly precondition the environment for heavier and more intense snow.
Thank you. And then Bob Robbins asks, you ever see diurnal effects in LES? Nice. Well, as far as I have studied the data, lake effect systems are short-lived, but we do see diurnal in the terms of elevated mixed layers. And maybe Dr. Kristovic can talk more about that.
Okay, sorry, I didn't quite hear didn't quite see the question. Could you repeat
So
it?
the question is by Bob Robbins, asks about ever see diurnal effects in lake effect?
Yeah, it's actually that's a really interesting question. We've done some work on that, quantitative work on that in the Western Great Lakes, where we tend to see lake effect greater intensity and more snowfall in the morning hours when the air lake temperature is the greatest. But interestingly, once you move inland away from the lakes, radar studies suggest that might reverse, that you have a well-mixed layer moving over the land. A little bit of heating from the surface can prop up convection in the afternoon. So it's not straightforward. It actually varies with location quite a bit.
Thank you. And then an anonymous attendee asks, is it okay to share the slides with the audience? And if yes, where can we get them? Maybe Gideon can answer it. This presentation is being recorded. That much I can say.
That is
And
correct.
just like any other AMS webinar, you can actually find them on the AMS Weatherband website. So as for the slides, I'm not sure if you can share the slides.
You should certainly feel free to contact any of the speakers here. I'm sure we can. We'd all be happy to share what we have and talk with you about it.
Yeah, if you email me, I can share the entire slide deck with you.
Wonderful. Thank you, Rich.
Sudhir, there is a question on the chat also.
Oh, yes, I was just about to read that by Mike Evans. When do Tug Hill lake effect storms result in large blobs of snow covering a large area of the hill versus when are more distinct banding structures observed? And how does this affect snowfall forecasts? Wow.
Maybe I can try to answer that. And my opinion is that the biggest discovery really in owls is how this narrow but very intense bandedness develops along the long axis of the lake, right? These lower eastern lakes, Erie and Ontario, sometimes have the wind flowing such that a band that is really much more narrow than the lake itself develops, where there is a very efficient circulation such that the snow downwind of the lake is really concentrated in a narrow area. And if that circulation persisted, that wind direction and strength persist over some time, you can really have extreme precipitation. And that's where lake effect snow really becomes important societally, right? It becomes an extreme event that has real impacts. So,
and another follow-up questions by Mike Evans. What conditions result in much more snow over the hill versus along the coast? And does wind speed have anything to do with it? That is, stronger winds result in more snow further inland over the hill?
Yeah, maybe I can comment on that. Peter Veals and Jim Steenberg has done some really nice work on that, looking at longer term data sets beyond just owls and looking at radar data and seeing how the pattern of lake effect, both over Tug Hill and over the mountains of Japan, vary with factors just like that, with the wind speed, with the stability of the incoming work. And yeah, you see shifts in where the precipitation maximum lies depending on the strength of the winds, but also modulations based on how stratified the atmosphere is. And if it's very stable, particularly with taller mountains like Japan, the flow can get blocked by the terrain, and that can really push the precipitation maximum upwind, even all the way out over the water.
Yes, thank you, Dr. Minder. Another question by Joe Phillips. Did any owls results contribute to better understanding meso-low formations and their propagation?
Well, what are meso-lows? Polar lows are probably more confined to open water. There have been a few observations, I think, over Lake Michigan, but then the much smaller scale shear-driven circulations that Jeff Frame talked about, they are observed and I guess better understood as a result of the owl's work.
Right. Yeah. We see the mesovortices. Those are about a kilometer or less, but there are also some mesoscale low pressure or mesoscale vortices we have observed over all the Great Lakes. A lot of them tend to form on the concave shoreline, either the upwind or the downwind shore, just because of the shoreline geometry there. We did not really observe those very well during owls, but we did a predecessor project with only one radar back in the winter of 2010-11, and we had a pretty big mesolow come right over us. And I did notice that as that came over, we actually wrote this up, that the snow changed from from aggregates over to snow pellets as that happened. But we really didn't get any great observations of the larger 10-kilometer plus scale vortices forming during owls, at least on dual Doppler.
Thank you, Dr. Frame. Another question by Caitlin Justmonth. I know entrainment CAPE has garnered increased attention as a parameter to use in forecasting summertime thunderstorms. Do you see this applying to LES as well?
Well, I actually taught this in class last semester, so I'll start with this. I actually have the equation up in front of me. I saw the question. It's well, we'll just say it's pretty involved. We'll just a little sneak preview here.
Wow.
But basically, what Entraining Cape does is, like Caitlin said in her question, is that it takes into account the loss of Cape due to buoyancy, or I'm sorry, due to entrainment, and it also takes into account the effect of updraft width on entrainment. That is, the more narrow an updraft is, the greater it will entrain because it's narrower. Whereas if you have something that's a lot wider, the center of that will be a lot more sheltered from entrainment. Now, in doing this, they were only in their derivation, they were only kind of looking at cylindrical updrafts like you would see in a supercell. How that might apply to a band, you would see a little less entrainment, I would think, with that. And then the other thing, how they account for entrainment, is they have this end Cape factor, this Cape that's lost to entrainment, and this is all work done by John Peters and others. He's at Penn State. This is not my work. But basically, because of the exponential increase in saturation mixing ratio or saturation vapor pressure with temperature, the effective entrainment is worse, not only in drier environments, that's obvious, but also in warmer environments. Simply because, again, that saturation vapor pressure increases exponentially with temperature there. So, for example, a 10 Fahrenheit dew point depression at 80 degrees versus a 10 Fahrenheit dew point depression at 10 degrees, you're going to have a higher relative humidity actually in the colder environment as a result of that. So that would help temper this somewhat, but I think, sure, would it improve the calculations? I think it would. But I think because of the often banded nature of these things and because of the colder environments, it wouldn't be as great as something like a supercell, or certainly a supercell penetrating into a very warm, dry, elevated mixed layer, now not off an upstream lake, but off of the Rocky Mountains, the elevated mixed layers you see on the plains. So hopefully that helps.
I will just, if you'll mind me chipping in quickly, in addition to that, there is some work on entrainment. A recent student, Sofia Sagrestano at ULI, University of Illinois, has done some work using LiDAR observations to estimate entrainment. And Sudhir helped a lot with that as well. And you raised, Caitlin, a question that I think easily you could get a PhD work on if you really wanted to. It's a great topic.
Yes, it is. Another question by Samuel Mindel. How do you begin to quantify those turbulent plumes of moisture or warm air from the lake in WRF? That's a challenging question to modelers.
Yeah, I mean, I'll say in the scale of simulations that my group has mostly been doing, and the type of simulations that are used in a model like the HER, the kind of operational mesoscale models, those turbulent processes are entirely approximated through what we call parameterizations. We have to make a lot of assumptions about relationships between larger scale variables and those smaller scale motions. But kind of what we've been finding is that the uncertainties in those parameterizations are pretty big and have big impacts on lake effect, particularly what's going on right near the surface, in the surface layer, not even up to the boundary layer, because then things like the roughness of the water and the sea state can even become important. We have done a little bit of work in collaboration with Jim Steenberg's group at Utah, using what are called large eddy simulations, which go down to maybe 100 meter grid spacing, where you're still not resolving fully the turbulence, but you're resolving the larger turbulent eddies that are moving heat and moisture through the boundary layer. And and one of Jim Steenberg's students did some great work on that. I'll drop them into the chat with these amazing simulations, 100 meter resolution, where you can see how the convection comes together and organizes. And I think we learned a lot about those.
Thank you, Dr. Minder. And then the last question, I see Dr. Gates is answering it. You want to just answer it now, Dr. Gates?
Yeah. So first of all, did we study open cellular convection in owls? Not really, because the lake is probably not quite big enough for that to develop, and it was not part of the experimental design anyway. We focused on the short fetch and the long fetch systems. And then with regard to instruments failing on the King Air, well, we had some icing on some of the probes, making measurements unreliable. And we were in general concerned about airframe icing in the more intense bands that we crossed in a lawnmower pattern, especially at low levels, because aircraft performance. So we generally flew at relatively high levels in owls and used the radar data primarily.
Yeah, and on ground-based instruments, well, another thing with the King Air 2 is that the Penyan Airport, which only has a north-south runway, and when you have prevailing winds out of the west, that could that sometimes presented takeoff and landing issues. That if you have too strong crosswinds, you can't do that. Some of the Dows, not so much the Dows, but some of the other surface vehicles occasionally got stuck. When something did go off the road in a heavy snow band, everybody was fine, but there were some locals nearby, and they took us in and they gave us soup or something, and it was real nice. But sometimes there were some vehicles that got stuck. The Dows, just like any long-term operation, sometimes, things would break or, something would go wrong in the transmitter and that would have to be fixed. So not all of those were always operational. I'm trying to remember if the MIPS got stuck once. It might have, because that was usually in the middle of the band. And again, it's just, a lot of wind, a lot of cold, a lot of snow. And the students were a lot more in the snow than all of us were, than at least some of us were. I was mainly in Oswego, so.
Thank you, Dr. Frame.
I'll just add that it's not easy doing an experiment like this, as everyone can attest. Going out into the conditions, I can remember a truckload of students pulling a trailer, driving from Geneva to Tug Hill in order to support the University of Utah experiments, and snowing and lightning and just as as dastardly conditions as you can imagine. But it's exciting at the same time. It just for those of us who pit ourselves against that challenge, we had to wipe the drool from our mouth from enjoying ourselves so much. But we had it's some of these instruments, like the signal processing units for radiosondes, are not meant to be operated below 50 Fahrenheit. So whenever you have the trailers open to launch your balloons and stuff like that, you're putting things around. We're literally putting hot hands all over the place and snow is blowing in one door of the trailer and out the other, and it's exciting. It's an exciting opportunity to just get out there in the weather and, let it in your face. So,
yeah. One time, the MIPS trailer, University of Alabama, Huntsville, the trailer axle broke, maybe because of all the salt on the road that had been driving back and forth different sites. And, Kevin Nubb decided to take measurements from that spot right on the road.
I've seen 89 tornadoes, all intentionally, and I'll say that lake effect snow research is a lot more challenging weather-wise than I think doing research on severe storms.
I actually never realized before this how bad condensation freezing inside of trailers is bad, but it's even worse when you heat up the trailer and you start getting rain on the inside of the trailer. So.
Yeah, like Apollo 13, right?
Yes. So great folks on here that have done this.
I'm really surprised Dr. Molesky was able to retrofit U-Hauls in their campaign.
You have to be able to fill the balloon somehow. So the U-Haul is a good way to keep it enclosed so you can, be out of the elements a little bit more. But you do have to get the U-Hauls around in the snow, which is tricky.
Oh, yeah,
I think one of
tricky.
our more frustrating things that we kept running into is, we all have our cell phones out for communications or pictures or, documenting times, and the amount of times, you get snow in the charging port and then your phone shuts off and everyone's inside, like with their phone in front of the heater trying to get their phone turned back on.
Wow.
an extra added piece of challenge that I wasn't really thinking about beforehand.
Not only the instrumentation, but our cell phones needs to be upgraded
Yeah.
as well. Yes.
Asud here. While we still have a good number of people on, I just wanted to take an opportunity to thank Gideon Allegado, who is the AMS logo that you see there, working behind the scenes and keeping things straight. He's been indispensable in helping us prepare for this.
And I want to thank Rich
Thank you.
for organizing this. Thanks for the initiative, Rich.
Yes.
Oh, it's my
And-
pleasure to see everybody again. And I saw one comment that said we should have a Winter Lake Effect webinar
Part
too. Yeah, so maybe we will. You know, we
Maybe-
can talk all day about this. We're not tired or proud.
Yeah, make it like a short course or something, AMS short course.
And I see there's one last question there from Caitlin, and
yes.
thank you again, Gideon and Bart and Rich and everybody. But forecasting lake effect bandwidth, I'm not aware of anything. But that could be a potential graduate school research project.
Yeah, Jeff, in some of my research, we do find that the width and the mesoscale structure, does change when you vary the turbulent fluxes and the microphysics. But that's something I think I agree. There's a lot more work that could be done, seeing the interplay between the fluxes and the microphysics and the mesoscale dynamics. And so that's something I've wanted to look into more, but I haven't found the time.
Right, and we collected so much data during this project. It's all on the archive that anyone can use it.
Yep. Well, thanks everyone for joining us. I mean, there's still 105 participants that are about ready to log off. And
If anyone wants to add a Q&A or something, I guess, are we okay to stay back for a couple of minutes? I mean, it's up to them. There's one comment by John Trustel. Honestly, I don't understand many of the words. Way back in the day, while taking data in the unheated bread truck, I don't know what a bread truck is, the 5 1/4 inch discs, I don't know that either, shrunk more than half a track, and data recording stopped. So that would have been a challenging campaign, I would assume.
Yes, definitely.
The 5 1/4 inch discs; those are the ones that were actually floppy discs.
Ah,
The ones that actually were floppy, unlike the 3.5 that were not floppy.
wow. How much data can they have? Like one pass?
I know the 3.5s were 1.44 megabytes.
Wow.
The 5 1/4s, I think, were less than that, but they did have 2 sides to them, from what I remember.
Were they 512, maybe?
That's a good guess.
It was enough to play Oregon Trail.
Yes, it was.
All righty. Well, folks, did you have anything else to wrap up the occasion? Anything that it sounds like there is demand for another outing here with everybody. So yes, please keep us in mind and this opportunity in mind, because I think if there is demand, we should supply, right? So but yes, thank you.
Rennie Selkirk typed into the chat, yes, I have a question. Please go ahead.
While that's coming up, I think maybe our next webinar should be to organize the next major field project on lake effect beyond the Lee project and beyond ELS.
Maybe whole of US, now that I saw lake effect happening in Dallas as well. So next Arctic blast, you can actually deploy everything everywhere. Oh, Rennie can't unmute. Let's see if we can. Maybe try now.
Oh, okay, thanks. I happen to be sitting in South Towns in Erie County right now, New York, and I was intrigued by the statement about how the snow bands persist on shore, whereas one might think that they should be limited to the regions over the moisture source. Could one of you speak to that phenomenon? It's obviously a very distinctive feature of certainly Western New York storms. I'm not familiar with Tug Hill.
Fair amount of work on that. Maybe Justin could do it best justice. No,
No, go ahead, Dave.
I put you on the spot there. Sorry. Yeah, actually, it's really a complicated group, and I know Penn State group as well as some others focused a great deal on that, and a lot of it has to do with how differential advection, how the cold air from lake effect might propagate further in at the top of the boundary layer. Cold air propagating in where the air near the surface stays a bit warmer, so you can get convection being generated well inland. But I don't know if anyone is. Oh, go ahead. Sorry.
Yeah. And that's combined obviously with a roll cloud aspect to it, because these snow bands are incredibly sharply defined, and you know, they move around, but they are very, very sharp.
Yeah, I think that the roll convection really helps to sustain the organization. That helps the further propagation.
Right.
You know, whenever I was living in north central Pennsylvania, I can remember many times we would see the effects of these horizontal roll convection coming through the area. So it helps to organize and sustain them once you get the horizontal roll there.
And also we found that when, at least in some cases, when you have a elevated mixed layer, such as associated with a extratropical cyclone, it's a lake enhanced snowstorm, some people call them. You know, there have been several cases where in those conditions, the lake effect went inland, you know, quite a few tens of kilometers. So it's a complex question. It's a good question.
There's a paper just published by Stephen Graybush et al. On elevated mixed layers. So, and I think it's in that list that you provided, Dave.
Yeah.
The
And
one in the
paper
QR
just
code.
Yes, another one just got accepted like yesterday.
Yeah, on that topic. So
Cool.
great.
Yeah, I'll take a look there.
Yeah.
Thanks.
Yeah,
Thanks, Rennie, for the question. That was
good question.
All right. Bob Robbins mentions that in future maybe more detailing on modeling. Definitely.
I saw Phil Bergmeyer was on and wished Owls a happy 10th anniversary. He was involved in Owls, if you remember, and helped us with the ice crystal photography. Yeah. Hey, Phil.
Oh, he's on.
Can you hear me?
Yes.
Hey, Rich, how's it going?
Good.
I don't have much to say.
Thanks for joining. Appreciate you joining.
No problem.
This gives you an idea of how close people get when you're doing field work together, especially in trying conditions. You know, you all get to know each other very well, and you know, so it's good to see Phil and some other folks that have noted they were involved in the project.
Yep, thanks for doing this.
All right. And then there was an anonymous question. Does orographic lifting play a part in this?
Yeah, I mean the short answer is yes, but it's not the whole story. That was what we found, is that, you know, in the work by Steenberg and Campbell, they find that even if they do a simulation where they remove Tug Hill, you still get a local maximum precipitation. So it does help to enhance it, but it's not the whole story. And they've explored all sorts of variations in lake geometry and terrain geometry to kind of map out that parameter space.
Okay, so if there are no more questions, let's thank all the panelists one more time. It has been a very, very great discussion. 1 hour is not doing justice, I would say.
So thank you, everyone.
Yeah, thanks everyone
Yes.
for being
Thank you,
on.
Ron.
Really appreciate it.
Yeah, thanks a lot, Gideon, too.
Thank you so
Thanks,
much for
panelists.
your time and your work, everybody.
Bye.